Hello, welcome to today's webinar. My name is Sherry Kraber. I am from StatEase Incorporated, and we are going to talk today about the diagnostics associated with analyzing DOE data. I am going to start over. I had some audio difficulties. So my name is Sherry Kraber, and we are going to talk today about the diagnostics associated with analyzing DOE data. Thank you all for attending with me today. To prevent audio disruptions, we're going to keep everybody muted. If you have questions, I would definitely welcome you to put them into the questions panel. I will keep an eye on that, and I will try to answer the ones that I can. If I cannot answer your question immediately, I will reply via email as soon as I am able. You can also send your questions to stathelp@statease.com, and our group will definitely be happy to answer them. So StatEase Incorporated is based in Minneapolis, Minnesota in the United States. We make design of experiment software and do DOE training to try to keep all of our researchers and scientists up to speed on the best practices in design of experiments. If you want some additional information, we have our YouTube channel, which always is loaded with recordings of all the webinars we give. And we also have training offerings. We have our comprehensive training classes, as well as a new essential series of short courses. So those are available for you individually or for teams if you are interested. So let's get into today's topic. We are going to talk first about why do we care about diagnostics? Well, let's go back to the very purpose of why we do a designed experiment. So you have a type of system, a type of process that you work with, and you're trying to characterize this, trying to get a better understanding of how you can make improvements, get a better quality product, better quality results, maybe do things faster or simpler or what have you. So the goal here is to take some DOE data, which is a small sample of your system, just a small number of runs, and use it to create or build a predictive model. And this is modeling the larger system, the whole system. So we are using a small amount of data to try to model a really big system. And so, here we have our data, and somehow we're going to turn it into this prediction equation, which can be represented graphically. It can probably be optimized and all sorts of things. The statistical relationship between the factors and the responses is created using the statistical tool called analysis of variances, otherwise known as ANOVA. So this is an example of an ANOVA table where you have your model that's comprised of a number of terms, and you have the residual or error. And from this ANOVA, you generate F values, which are then turned into p-values. And we generally look at these p-values and determine, are these terms and the overall model, are they statistically significant? Are they reflecting something that is going to tell us what's going on with our system, this cause and effect relationship between the factors and the responses? So a key question is, are these F values and the corresponding p-values correct statistically? And also from these numbers, specifically the sum of squares values, we create R-squared values. Are those R-squared values correct statistically? Well, this depends on a number of things. So we come down to our ANOVA assumptions. Now, ANOVA validity assumes, number one, that the model is correct. That's a pretty big assumption. And we're trying to build a model that we hope is correct. But ANOVA validity assumes that the model is correct. That means we haven't put too many terms in the model. We haven't put too few terms in the model. We've used the right transformation and all these things. So we assume the model's correct. Then we also assume that the residuals are nearly independent, close to independent. They're never going to be independent exactly because of the way they're created, that they have a mean of 0, that the residuals have a constant variance, and that they follow a well-behaved distribution, which is approximately normal. If the model is correct, then the residuals should look like a sample of random variables with no signal remaining in them. They act as random variables would act. If these assumptions up here are violated, then those p-values, our squared values, your predictions, etc., are wrong. Now, to what degree that they are wrong, I don't know. That's something that the experimenter has to determine. All right, so let's first of all review some diagnostic basics, and then I'm going to follow that up with a case study where we will compare some good and bad diagnostics and one way of helping them out with the transformation. So a fundamental thing, we are talking about this thing called a residual. So what is a residual? The residual is the difference between the actual data and the predicted value. It's characterized by the letter E for error, and it is the difference between the actual and the predicted. If we look at a set of data, fit a linear model through this data, the residual would be the difference between what we actually measured and what we predict it to be. So these little differences all along the line. So these would be raw residuals. Now, there are reasons not to use the raw residuals to verify the ANOVA or to create all the diagnostic graphs. And a couple reasons. One, they are sensitive to either underfitting or overfitting the model, which means you have too few or too many terms in the model. And the variance of the raw residuals is not constant. So in general, we don't want to use these. So what should we use? Well, there are two types of residuals that are better. The first one is the internally studentized residuals, otherwise called the standardized residuals. This is the raw residual divided by its estimated standard error. Now, this type of residual does give us that property of non-constant variance, but it still does not follow a t-distribution. And here is the mathematical calculation for it. I am not going through the math. You can find the math and how to use these in any standard statistics textbook. So we are not focusing on that here. Externally studentized residuals, otherwise known as deleted residuals, adjust the studentized residuals to drop the ith data point. In this calculation, here's the minus I. So we leave out the actual value for the residual that we're calculating, and just do this calculation over and over called a deletion statistic. It's pretty cool. It corrects for non-constant variance, as the other one does, but it also then follows a t-distribution, which converges to the normal distribution. So we can then do a quick normal probability plot of the residuals and see if they follow an approximately normal distribution. You know, it's not expected to be perfectly normal because it's not. It's a t-distribution. It's not a normal distribution. So these are best for verifying assumptions. Oh, one other note is because it's a deletion statistic, it's also sensitive to points that do not fit the model. So it's also helpful for finding those outliers. All right, so just a quick view of the graphs that we'll be looking at more in depth as I move on. The first graph on the left side is the normal plot of residuals. And so we can see here that we have a little bit of up and down scatter. We are watching for large variations of normality or large violations of normality, maybe a big S-shaped curve. The middle graph is our residuals versus predicted graph. We're going to look for a non-constant variance across the range as our predictions go from smaller to larger. And then the residuals versus run is the third graph, where we can watch for time-based trends or patterns. And then both of these graphs have the red lines on them where we are doing a statistical calculation looking for outliers. So if we have points outside those red lines, those would be outliers. All right, so let's dive into a little case study here. This is our case study with a twist. This is a oil drilling operation. The drill in this process is driven by a long pipe, and the pipe is hollow. It carries a water-based mud down the hole, and it helps carry off the pulverized rock and lubricate the drill bit. And so the whole goal of this was to increase the speed at which we could drill these holes. So the input factors and ranges are the load on the drill, a flow rate, the speed of the drill, and the type of lubricant or mud that they used. So I have this file opened up here, and we are going to analyze it, start the analysis. And the first thing we do is use our half normal plot to divide our effects, our terms, into the two groups. The group that we want to be in the model and everything else that we want to help us estimate the error of the system or the residual. So we're going to take all of these terms that jump off that line, and we put them into the model of the ANOVA. So we've got them here, and we've got our terms, 3 main effects, and two-factor interactions. And over here we have our adjusted and predicted R-squareds, which look just great, 0.94 and 0.889. So those are excellent. All the statistics here on the ANOVA look super. You know, there are no obvious problems with these values. So the next step is to do a quick look at the diagnostics. And when I teach classes, I tell people it usually takes you a few seconds to look at diagnostics because in most cases, they will fit all the patterns that we want. This is not one of those cases. So we are going to go back and compare each of these. Okay, so let's start with the normal plot of residuals, what it should look like. What we are doing on here is we have a normal probability paper, and we are plotting the residuals from lowest or smallest residual to largest residual along this normal probability paper. If the residuals fall on a straight line, then we can declare them normally distributed. Now remember, I said that these residuals actually aren't expected to be perfectly normal. They're actually following a t-distribution. It's just a tiny adjustment. But we can use normal probability paper to approximate this, and it should do pretty well. Basically, we want the residuals to have a single peak. So if we plotted this actually as a normal that curve, it would have just one single peak, roughly symmetric, and your tails would die off rapidly. Now, the ANOVA is robust to moderate deviations from normality. So there is no need for a formal test like the Shapiro-Wilks test. People ask us for that all the time, but that would be a little bit too harsh. And there's actually, we've seen it, we've taken perfectly good sets of data and applied that Shapiro-Wilks test, and it may fail that because it's a little bit too precise for what we need. We just need to be moderately normally distributed. A little bit of up and down scatter is not a problem. The ANOVA is robust to that. You can find this statement in textbooks like from Douglas Montgomery or Myers and Montgomery Response Surface textbook. Both have those statements in there. Okay, for the well drilling experiment, this is the graph that we actually have. This is an obvious failure. Definitely not what we want. We have 2 points that are jumping off the graph, and that gives the appearance, you can see, of this S-shaped curve. So this data set fails the assumption that the residuals are normally distributed. Okay, so let's go on to the residuals versus predicted diagnostic graph. Now, on the x-axis here, what we are plotting is our predicted values. So we are plotting every residual against what we predict it to be. And so predictions are going from smaller to larger. And this plot should be a random scatter of the points. We are looking for systematic patterns, maybe evidence of increasing variability as the predicted value increases. So we might call this a megaphone shape or a horn shape. If it were here, it's not, because we have a pretty straight amount of variation from lower to higher predicted values. Just basically a random scatter. That's all you need. Look for patterns. So I have seen a pattern such as all the beginning, the first half of the runs were all above the line and the second half were all below the line. That tells me that maybe a block is needed to remove the signal that's still in the residuals. So that is, again, what we're trying to do is look for any signal, any patterns that remain in the residuals that has not been accounted for by the terms in the model. Okay, our well drilling experiment gives us a predicted versus residual graph that looks like this. You can see that the residuals are tightly constrained to the 0 line, as you're making small predictions, and they grow larger and larger as you're making larger predictions. Now, I'll point out, or go back to a reminder, our response is the advance rate of the drill, which we're trying to maximize. So where do we want the data to be? Where do we want our best predictions to be? We want to be able to predict really well up at this high end. And yet this is where, you know, we see some evidence that, oh, these points are outside the red lines. So a first reaction when people see points outside the red lines is what? Those are outliers, and I have to remove my outliers. Oh my gosh, people, no, think about it. If we removed these two outliers, they are the best data points that we have. The best data points that we have. Okay, so the definition of an outlier is not that it's bad, it's that it's a point that is not being explained well by the model. So this model is not predicting these points well. Okay, are the points wrong? Not necessarily. It might be the model that's wrong. And that's what we really have to consider, is that the model in this case might not be as good of a model as we can get. Okay, one more graph, the residuals versus run order. What it should be, you know, just it should show no patterns or trends. Again, watch for any clumps of data above or below lines. Watch for anything going upward or downward, and watch for points that are not predicted well. So that is our well drilling experiment, where we have no particular trends, so that's good, but there are 2 points that are not fit well by this model. We can call them outliers as long as we recognize that an outlier is not the same as bad data. It could also be bad model. Okay, so those are the primary diagnostic plots that you want to look at. We have one more plot that really helps us check the model itself. Is this model done in the right scale? So that's called the BoxCox plot. It's in the lower left-hand corner in the Design Expert. Here, I'll just show you. Jumping back to Design Expert. So we're down here in this lower left-hand corner with this BoxCox plot. And it should simply say recommended transformation is none. And what this plot is doing is it is taking your data and it is raising it to a certain power, and that power is called the lambda value. So it takes your, well, let me start with a simple one. Lambda of 1 is the 1 power. So we have, if you have a value of 5, 5 to the 1 is still 5. 10 to the 1 is still 10. So a lambda, or a power of 1, is no transformation. And in this example of what it should be, we are good with no transformation. But under the covers, Design Expert takes your raw data and applies this series of power transformations to the data. And for every location, it calculates the residual sum of squares. So what's residual sum of squares? Well, that's error. So it fits your model, calculates the error, puts it on a natural log scale just for scaling purposes, and plots it. Okay, then it goes to, the next power. It takes your data, raises it to the -2 power, fits your model, calculates the error, and plots that error. Goes to the -1, fits your data to the model, calculates the residual error for that model and plots it. And so we just do a whole series of transformations to your data. Now, what would be the goal of our error against a model? Well, we always want to minimize error. So wherever this BoxCox graph bottoms out, that would be the transformation that gives you the least amount of error. So that would be the perfect transformation, right here where the green line is. Now, for every statistic that we calculate, we also want to calculate a 95% confidence interval. So the red lines, shown here, the red lines are that 95% interval, and basically any transformation within the red lines is statistically good. It's going to be statistically good. So when we have our 1 or lambda of 1 or power 1 power within those red lines, then we don't have to make a change. There's nothing statistically to be gained, even though it looks like it's a lot less. You can try it. You could try putting on whatever. This is about a -0.5 roughly, and it's just not going to do much to improve your analysis. So as long as 1 is within the red lines, then the software is going to recommend the transformation of none. Just stay where you're at. Okay, let's look at the well drilling example. So here we are with our well drilling example, and you can see that the 1, no transformation, is now outside of our confidence interval. Our best transformation is at about roughly -0.25. And then there is an interval here. And within the interval is the log transformation. Lambda of 0 is represented by the log transformation. So the recommended transformation is a log. This is saying that the model we currently have with no transformation can be improved. We can reduce the error in our system by applying a log transform. So we're going to reanalyze the data using this scale. Okay, now, before we jump into that, I make one more comment. We have looked at the normal plot of residuals, the residuals versus predicted, the residuals versus run. Those are the 3 diagnostic plots. Then we have used the BoxCox plot to check for the need for a transformation. Okay, so those are the things that are absolutely critical. What about this corner over here, this lower right-hand corner? Okay, these graphs are influence graphs. They are not diagnostic graphs. They are influence graphs. They measure how much influence a specific point has on certain properties. Every one of them is a different property: Cook's distance, leverage, DF fits, and DF betas. And these properties are things like the fit of the model, DF fits, and DF betas is the coefficient estimate. Now, high influence does not mean that it's a bad point. Let's say that you have influence on the decision that your friend makes. Just because you have a lot of influence on them, does that mean that that is bad influence? No, you might have good influence on your friend. I hope you are a good influence on your friends. So these graphs down here can be used if you have outliers. You might come down here and check on the amount of influence that they have, and if they have low influence, then they're probably not going to influence your model or coefficients a lot. If they have high influence, they will affect things more, but that still can be either in a positive direction or a negative direction. So just because you see things having strong influences does not necessarily mean they're bad. So I have to say that because we will often have perfectly good sets of data, meaning all the diagnostics are good. There are no outliers. And yet people come to these influence graphs and they poke around at them and they discover that some of the points are quite far away from the others. And then they think that they have outliers. They're not outliers. They're just more influential points than others. But if you didn't see any problems with the diagnostic graphs, then you really probably shouldn't be looking at the influence graphs. So influence graphs are another level of just trying to understand your data more. Okay, so I just wanted to make that one point before we finish up with this analysis. So we discovered that a log transformation is recommended. And so we would go back to our configure button and put on a log transformation. Which one, the natural log or base 10 log? It doesn't matter from my perspective. It doesn't matter. So I'm going to use a base 10 log and then redo the analysis. You have to start over. There's a big change here. Now we went from 5 effects to just 3 effects. So under this new scale, it turns out that only the main effects are needed. Those interactions were being used to attempt to model those extreme points. And if we put everything on a log scale, then we don't have that extreme difference, and so we can just use linear effects. These are nice and strong. Our F value has actually increased from the original value of 48 to now 206. So a huge improvement in the F value, and the R squared values have also increased dramatically. Now, under the log scale, let's see what happens with diagnostics. We have now straightened out this normal plot of residuals. We have gotten rid of that megaphone shape or increasing variance problem. Our residuals versus run is just a random scatter. And those points that were previously outside the red lines are now being comfortably fitted. So they're at about plus or minus 2. So really good. And now the BoxCox says the recommended transform is a log, and we have done a log. So our blue line, let me just blow this up. I'll make this the only graph. Our blue line is comfortably within the red 95% confidence interval. And so we are good. I like to tell people when what you have done, current transform, matches the recommended transform, then you are in good shape. And there is no need to do any additional work with transformations. Okay, so our new model has fewer terms, but it actually predicts better. It explains more variation. All of our diagnostics now look as good as they're going to get. So let's have some final comments here. If you have any questions, you can put them into the chat box. ANOVA validity assumes that the model is correct and the residuals are nearly independent, have a mean of 0, have a constant variance, and follow a well-behaved distribution that we check via normal probability. I want to emphasize this last one. There is incorrect information floating out there that people often say, well, design of experiments has to be done with normally distributed data. That is flat out wrong. Your raw data does not have to be normally distributed. It is the residuals that should be approximately normally distributed. As shown right here, our original data followed more of an exponential scale, and we adjusted for that by using a log transformation so we could get a good model. But the raw data definitely does not have to be normally distributed. It is those residuals that we are concerned about. And in the end, if the model is correct, the residuals should have no signal remaining in them, so no particular patterns existing. Now, what if, even after you've done this or there is no transformation recommended, what if the residuals remain messy? Well, going back to the science, could there be any additional variables to consider? Any other factors that weren't included in the experiment? Then, you know what? This DOE is collecting a small sample. Perhaps you just had some bad luck, and in this sample, you happen to have some unknown random effects. You know, something might have floated through the system at that point. That can happen. I highly recommend doing confirmation runs. I mean, it is pretty much a must do. Use the model as it is, even if it's somewhat messy. Pick your best conditions and run them. Then compare those results to the predicted values that you get from point prediction. Find out if the model is sufficient. It might not be perfect, it might be a little bit messy, but find out if it's sufficient. If all else fails, you might need to do a replicate or collect more data to enhance the information. It really depends on the risks of using an imperfect model versus spending more money to get more data. You know, it's once again going back to, we are collecting just a small sample that we are trying to use to predict a big system, and it's not always perfect. We're just trying to do the best that we can. All right. Somebody asked if this session is being recorded, and yes, it is being recorded. It'll get posted up to our YouTube channel and to our webinars page on our website by tomorrow. The person who does it is out today, but it should get posted by tomorrow. So you can check there to go back and review this. I also highly recommend this playlist. If you're new to DOE, it has the collection of great topics that are just designed for basic to intermediate level type of topics. If you want some online training, you can go to our website and register for some of our academy classes. They are all free of charge. All right. So I want to thank you for coming. I appreciate your time today. If you have further DOE questions, you can email them to stathelp@staties.com. If you do have any sales questions, you can send those to our sales@staties.com email. And I want to thank you all for being here and hope you have a wonderful rest of your day.